2.3 is about identifying functions from numerical patterns, or basically from inputs and outputs. So we're going to see a lot of input-output tables. If given sets of corresponding inputs and outputs, how can you identify which type of function they fit and find other function values? And we're only going to deal with 4 different types of functions. We're going to deal with linear functions, exponential functions, power functions, and quadratic functions. And what I've given you here is some copying and pasting that I did out of the textbook. So we'll come back to this as we work through our exploration. So keep it handy. Have the exploration out. So some of this I already did for you because I know that you all know how to put functions into your calculator and get out a bunch of values. So I decided it would be a waste of time to have you guys do that. Let's just get right to the meat of all this, okay? So number 1, you can see, you were given this exponential function. They wanted you to find all those f of x's. I wrote those in for you. You are welcome. Okay, so number 2. If x1 equals 4 and x2 equals 6, how does f of x2 compare to f of x1? Okay, so we're looking at when x is 4 and when x is 6. Now, there's a lot of different ways that you can compare things, but in this situation, what we want to do is we want to actually create a ratio. So 145.8 divided by 16.2. Sometimes when you compare things, maybe you'll want to add, maybe you'll want to subtract. And what I would let you guys do, if we had all period to work on this, is I'd let you figure that out. I know that we want to compare the ratio of these two. We want to, compare those two using a ratio. So when I actually divide 145.8 divided by 16.2, or y2 divided by y1, I end up with 9. Okay, and now let's see if that holds true. If I talk about x1 being 8, so now this one, and x2 being 10, then what's true when we compare, y2 and y1? So we're going to do a similar type of thing. I'm going to put that 11,809.8 over 1,312.2. And again, when I divide those in my calculator, I get 9. So what I'm noticing is that when I'm going from one to the next, I'm really multiplying by 9, right? 16.2 times 9 is going to give me 145.8, since 145.8 divided by 16.2 is giving me 9. So, and this is, a lot of what math is looking for patterns. So you might have looked at this and said, well, maybe I can add something continuously. Maybe from 1.8 to 16.2, I notice that that's a certain change, and then can I add the same amount to get 145.8 from 16.2? That's not the case. Here it's actually multiplying. And the same thing was true here, so I was able to multiply by 9. Okay, so moving on to number 4. So show in the table that anytime 2 is added to x, f of x is multiplied by 9. Okay, well, let's look at that. So I add 2 here. Is it true then that I multiplied by 9? Well, let's go ahead and check that out. So, if I take 1.8 and I multiply that by 9, am I going to get 16.2? And in fact, it is working. Okay, so there's another multiply by 9, right? Add another 2. We can see that multiplying by 9 works, right? And so on. Add 2. So there's this constant pattern that if I add 2 to my inputs, what I'm really doing then in my outputs is I'm multiplying by 9. So that's how you would show that. Okay, so we did that for number 4. Check. The property in problem 4 is called the blank property of exponential functions. Now, that's the first property that I gave you here. That's the add, multiply pattern or property of exponential functions. So what it's saying is that if I'm adding something to my inputs, a constant something to my inputs, and my outputs are, 9 times or the same amount multiplied together, let's see, that didn't come out very good. If I add a constant, the same constant, to every single input, and my outputs are the same multiple of each other, right? Multiplying by 9, multiplying by 9, multiplying by 9, then I know that I have an add multiply pattern, and I know that this thing is an exponential function. And in fact, if I were to graph it, it would look like this. So that is called the add multiply property of exponential functions. All right, so now we're going to do a similar thing with power functions. Let's see if we can figure out what the property is. You know, what is the pattern? All right, so for this one, we're going to show in the table all instances you can find where x2 equals 2 times x1. Okay, so let's see. So x2, well, for example, this is 2 times x1, right? So this right here is 2 times 2. Let's see. Okay, well, this would be 2 times, if I called my x1 4, then this would be 2 times x1, or 4. Let's see. 6, if I multiply that by 2, I'll get 12, right? So this is 2 times 6. Okay. Then show how g of x2 compares to g of x1. So if I take, for example, 320 and 40, what's the comparison there? So if I take 320 and divide it by 40, I get 8. Okay, well, let's see. I also did 4 to 8. So what if I take that 2560 and divide that by 320? I also get 8. Just to make sure that this is actually, that this pattern is continuing, using my my reasoning skills here. Let's see. So I went from 6 to 12. So let's see if the comparison works. 8640 divided by 1080. And in fact, once again, I do get 8. Okay? So we're going to complete this sentence. Multiplying x by 2, what does that do to y? Well, it multiplies the outputs, or the y, by 8, right? So I can see that when I went here, I got a multiplication of 8. Let's see, when I went from 4 down to here, I got a multiplication of 8. Now notice it's skipping, right? So it's not necessarily happening at every single output. Let's see, when I did, it also happened here when I doubled 6, right? Okay, so it happened 3 different times. Okay, so that tells me then, let's move up to 9. The property you observe in problem 8 is called the multiply-multiply property of power functions. Write a sentence stating this property. So what this is saying is that in a power function, multiplying x by a constant. In this example, our constant here was 2, right? We were looking for anywhere where we could multiply a previous x by 2 to get the new x. Multiplies y by a constant. And in this case, we ended up with that constant being 8, right? Okay, now that brings us to our next property, which I put in your notes for you, is the multiply-multiply pattern of power functions. They're interchanging pattern and property. Okay, so let's see. So they're doing a similar type of thing. They multiplied by 2, and you can see to go from 3 to 6, you multiply by 2, and from their first output to the second output, you multiplied by 8. Okay, now what other ones here can I multiply by 2? What other inputs? Well, I can multiply 6 by 2 to get this output, or to get this input, I'm sorry. Okay, and does it hold true then that the output, g of 6, needs to get multiplied by 8 to end up with g of 12? And in fact, it does. Okay, and that gives you that power function. Okay, moving on to a function that we're super duper familiar with because we've been working with it for, I don't know, since grade school. All right, so we're working with a linear function now, 7x plus 17. So I filled out all the values for you. So moving on to 11, show in the table 3 instances in which my second x, x2, is equal to x1 plus 4. Okay, so I'm going to take 2, and if I add 4, I get 6. Oh, let's see, how about if I take 6, I end up with 10. Let's do one more. How about from 8 to 12? That's also adding 4. Okay. Show how h of x2 compares to h of x1. Okay, well, let's look at this. Let's see if we end up with a constant pattern. So going from 31 to 59, how does that compare to when I go from 59 to 87? Well, I have a feeling, 31 into 59, that's like twice. 59 into 87, not quite twice. So I think that dividing or multiplying here is not going to work out for us. This is linear, which means that there's a constant rate of change, which means that, that slope is the same, and our slope is actually 7. So if I skip 2, right, my slope should end up being 7. So if I skip 2 here, well, from 31 to 45 was going to be 14. And so from 31 to 59 is going to be 28. Okay? Similar things should be happening here. From 59 to 73 would be 14, right? And I just skipped 2 there, so 14 divided by 2 is going to give me that 7, okay? Or I skipped 2 places, so now it should be a plus 28. So really what's happening here is each time I'm increasing by 14, okay? The same thing's going to happen from 8 to 12. Now again, I skipped 1 here, so going from 73 to 101, again, that's a plus 28. Okay, so we showed that. Complete the sentence. Adding 4 to x, well, what does that do to h of x? It adds 28 to h of x. Okay, we're going to use your findings in problem 10 to complete this following statement. The blank blank, what did I do on both sides here? I added, right? The add property of linear functions states that adding a constant to x adds a constant to f of x. Not necessarily the same constant, okay? Definitely not in this case. So I included an example of that in the handout to kind of summarize that. So that's the add pattern of linear functions. If I add some constant, and this one just goes between, from x1 to x2 to x3, which is usually how you'll see it, or usually how you'll come about it. So I see that the x is changing. It's increasing by 2 each time. Okay, and so my outputs I see are now increasing by 3 each time. So I'm adding 2 on this side, adding 3 on that side. That's what I mean by the constants won't necessarily be the same, right? So the constant I'm adding to the inputs is not the same as the constant I'm adding to the outputs. However, they are, definitely the exact same constant is being added to the outputs, exact same constant being added to the input. So hopefully that's clear for you. Okay, and that comes, I mean, that's from slope. That's what that is right there. There's your slope, 3/2. There's one more pattern, and it's not part of our exploration, but it's for quadratic functions. Then you're going to have a constant second differences pattern. So what's happening is on the inputs, you're adding the same constant, okay? Now on the outputs, and this is labeled wrong, there's first differences and second differences. The first differences were here. When I went from 15 to 5, I subtracted 10. 5 to 19, I added 14. 19 to 57, I added 38. Okay, so cross out this arrow. The first differences are here. Okay, so this is actually one of my favorites because I'll always look at something. I'll be like, okay, look, I'm adding the same thing on this side. Now, why is this being added differently? And they don't compare the same. Then I know it's time to go to the second differences. If that second differences ends up being constant, then you have a quadratic. So we have a constant second differences. So we go from -10 to 14, that's plus 24. Go from 14 to 38, there's another add 24. 38 to 62, add another 24. So we have that constant second differences. We know that it's a quadratic function. All right, last thing we're going to do is number 14 here. We're going to prove algebraically that if I'm given p of x and it equals this, and if x2 equals that, for any constant c, then p of x2 is equal to some constant k. So they use c and k for constant. So you got to get used to kind of those being interchanged. So it's going to equal k now times p of x1, okay, for some constant k. All right, so I am given that p of x is equal to a times x to the n, and that x2 is equal to c of x1, or some constant times x1. All right, then, p of x2 can then be written using this as a model. So we can say that it's a times, instead of just any old x, we're going to say x sub 2 to the nth power. Well, we know that x sub 2 is the same as c times x to the 1. Okay, so we can then say, okay, well then this is really a times c times x to the first power. And all of that needs to be raised to the nth, right? Because x sub 2 is being raised to the nth power. Okay, so I'm going to rewrite this a little bit. So I can actually say, well, this is really a times c to the n times x1 to the n. And then just rearranging it a little bit, I'm going to actually pull the c to the n out here times a times x sub 1 to the n. Now notice, a times x sub 1 to the n, or a times any x to the n, is going to be basically p of x. So what I've ended up with here is c to the n times p of x1. Well, now really what I've got, so c to the n, we could really consider this. We can really consider this to be some constant. Okay, we're going to see a lot of this when we get to calculus, okay? We don't know what c to the n is, but it's some constant that we're going to make a little bit more generic by calling it k. And this is really k times p to the x sub 1. And this is where k is equal to c raised to the n power. We don't know what c to the n is, but we're just going to call it some constant, so we're allowed to just substitute it in there for c to the n. Now we're going to do one of the evens from the problems that you'll get assigned. So on page 85, I'm going to do number 14 with you. So what 14 is asking you to do, so the directions are up here for 13 through 16, you're going to find the indicated function value. If f is a linear function, b, a power function, and c, an exponential function. And we are given f of 3 equals 80, and f of 6 equals 120, and we want to find f of 24. Okay, so we're going to need to make some input-output tables here. So once again, I'm looking for, so this is page 85. We're going to do number 14 together as an example. We are given that f of 3 equals 80. And we know that f of 6 equals 120. And we have to figure out what f of 24 equals in 3 different scenarios. First scenario being a linear function. Okay. All right, so first thing I'm going to do is I'm going to make an XY chart, or an XY table, input-output table. I'm going to start with what I was given. I was given that when I put in 3, I get out 80. When I put in 6, I get out 120. Okay, now from our notes, we know that linear functions have an add pattern. So am I adding some constant to my x values to get the next one? And if I am, then am I also adding some other value, some other constant to my y values to get the next one? So let's see. So it looks here like to get from 3 to 6, I'm adding 3. And to get from 80 to 120, I'm adding 40. So I'm going to continue this pattern going. That's how I'm going to do this. It's not that easy, but it might be easier sometimes than writing a function. Actually, I think writing a function would probably be easier, but let's just do that for the sake of recognizing patterns. So if I add 3 on to my last input, I'm going to end up with 9. Keep that going all the way until I get to 24. Okay, and then I need to add 40 to each one of my outputs. So I've added 40 each time, so I can see that when I put in 24, I'm going to get 360 out. So I can conclude then that f of 24 equals 360 if this is a linear function. Okay, let's try this for another one. So B wanted us to do it for a power function. So I'm going to start my table the exact same way. So I put in 3, I get 80 out. I put in 6, I get 120 out. Okay, now this is the power function. So let's see, the power function, the pattern is multiply, multiply pattern of power functions. So whatever I'm putting in is getting multiplied by 2. Okay, and then this, whatever the outputs are on this example, is getting multiplied by 8. So let's see if we can come up with something similar to that. So let's see. 3 to 6 is getting multiplied by 2. Now the question is, how much is 80 getting multiplied by to give you 120? And if you don't know that off the top of your head, what you can do is you can take, let's see, there we go. You can take 120 and divide it by 80. You get 1.5. Okay, so I'm basically multiplying here by 1.5. All right, let's continue that pattern going. So now I need to multiply by 2 to give me 12. And then if I multiply by 2 one more time, I'm going to get 24, right? Each of these are times 2. Okay, well, multiplying 120 by 1.5, well, that's 120, add half of 120, so that should be 180. And then, so that was a multiplication of 1.5. You don't have to write this. I just like to have that out there to show what I'm doing. And then 180 times 1.5, well, that's 180 plus half of 180, which gives you 270. So I know that here, f of 24 is going to equal 270. Okay, and we're going to do one more. Let's do it right under here. And this is the exponential. So starting with the same exact table. Now for exponential, this is where you have the add, multiply pattern. So we add a constant to our inputs, yet we multiply some constant to our outputs. So let's see if we can figure out what that is. So I'm going to add 3 each time, and we already figured out that this was going to be multiplied by 1.5. So it's not going to be as easy as this table up here, because here I was able to double and quickly get to an input of 24. These inputs are going to look a lot like the linear inputs, right? Because I'm adding. So I'm going to have 3, 6, 9, 12, 15, 18, 21. Oops, 24. Sorry, I'm off the page. 24. But now I'm going to keep multiplying on the right-hand side, all those outputs. I'm going to multiply them by 1.5. So, multiply this by 1.5, we get 180, just like we did above. Multiply that by 1.5, you're going to get 270, just like we did above. And then you might want to start using your calculator from there, because it gets a little bit hairy. Or, maybe you can use your brain. I used my calculator. And I ended up with 1,366.875. So f of 24, if this is an exponential function, is going to look like this. So those are my 3 answers.